For this lesson, we're going to go through a variety of examples of how we can compute limits algebraically or evaluate limits algebraically. So, always your first step, the first thing you want to do when you're asked to evaluate a limit algebraically, okay, try plugging in your number, okay? So our A value, the one that we are approaching. Let's look at a couple of examples where we can do that. So most limits, if you're just asked a pretty straightforward, regular old limit, random limit, this is the most likely thing to work. So let's say we have the limit as x approaches 0 of x squared minus 2x over x squared minus 6. Okay, so this is equal to 0 squared minus 2 times 0 over 0 squared minus 6, as long as the denominator is not 0, which it's not going to be. So this equals 0 over negative 6, which is just 0. A polynomial, any polynomial, generally remember polynomials are always continuous functions. So any polynomial, this is also going to work. So we have the limit as x approaches 3 of 2x squared plus 3x minus 1. Please notice that we're putting brackets around any terms that are added or subtracted, just so we know that we're taking the limit of all of these. Okay, so we will plug in 3 because that is not going to make any denominators equal to 0. So we have 2 times 3 squared plus 3 times 3 minus 1. So that is 18 plus 9, which is 27, minus 1 is 26. Okay, so next, we're going to look at what happens when this doesn't work out. And most of our most interesting examples are going to be ones that are a little different than just having where we plug in the number and it gets to where it's going, or a function that is continuous, where we're looking at a point where the function is continuous. So let's take a look at the limit as x approaches 3 of x squared plus 2x minus 15 over x minus 3. Okay, so what I do is when I take the limit of the numerator, so the limit, okay, and we don't write an equal sign because this is not going to necessarily be equal. So we have the limit as x approaches 3 of x squared plus 2x minus 15. We plug in 3, 9 plus 6 minus 15 is 0, and we have the limit as x approaches 3 of x minus 3 is also equal to 0. So what this means is that we have an indeterminate limit, okay, where we get something that's 0 over 0. Okay, it's not equal to 0 over 0 because 0 over 0 is indeterminate. We don't know what it is. So this is equal to the limit as x approaches 3. So the first thing we're going to try is try factoring, because we have polynomials in the numerator and denominator. It's a rational function. So this is the limit as x approaches 3 of x minus 3 over x plus 5 over x minus 3. Okay, notice I have to put the limit here, and I use that notation. I'm going to use that notation throughout until the point when I actually plug in the number. Okay, so I have x minus 3 factored out, so now I can cancel that x minus 3 because the limits will be the same. So this is equal to the limit as x approaches 3 of x plus 5, which is equal to 8. Okay, so if you have a rational function and you're going to a point, there are two options. This one, we had a factor that canceled. We had a 0 in the denominator, we had a factor that canceled, and we got a number. So that means that that was at x equals 3, we had a removable discontinuity. And so the point 3 comma 8, there would be a hole, but everything else around it would remain normal. If we weren't able to cross out the factor or remove the discontinuity and there was a 0 in the denominator still, then we would have an asymptote at that point, and the limit still would not exist. So here we have example 4. Okay. The limit as x approaches 2 of h of x. Okay, we're going to find this if h of x equals 3x minus 2 when x is not equal to 2, and 2 pi when x equals 2. Okay, so what does this piecewise function look like? Let's sketch a little graph of it. So it's 3x minus 2, so we have a slope of 3 and a y-intercept of minus 2. And at x equals 2, we would have a value of, there's a hole at 2 comma 4. And other than that, it is just a line. At the point x equals 2, we have a value of 2 pi, which is just over 6. Okay, so that point right there is 2 comma 2 pi. So we have 2 comma 4 is where the hole is, that the point at 2 is up there. So we want to know what the limit is of h of x as x approaches 2. Okay, so the limit as x approaches 2 from below. If you have a situation with a piecewise function, you're going to want to look at what's the limit from below and what's the limit from above. So the limit as x approaches 2 from below of h of x, okay, is equal to the limit as x approaches 2 from below of 3x minus 2. Because that's what the function is all the way as we are approaching 2 until we actually arrive there. So that's the limit of that's the function we are taking the limit of. So if I plug in 2 here, we're approaching 2 from below, something a little smaller than 2. We get 2 times 6 minus 4, so that is equal to 4. Okay, so now we have the limit as x approaches 2 from above of h of x, and when we're above, this is actually the same, this is the same thing. Okay, so this is the limit as x approaches 2 plus, because we still have the same function, 3x minus 2, operating here, and that is also equal to 4. When we have something just above, we're still approaching 4. Okay, so we have right here the two values of the limit that are the same. So we have the same value. So that means our limit exists, and it's equal to what this is equal to. So the limit as x approaches 2 of h of x equals 4. And we can show that by finding the two one-sided limits. Okay. Let's look at a similar example with a piecewise function. So we have the limit as x approaches 4. We're going to evaluate the limit of f of x as x approaches 4 if f of x is radical x minus 4 for x greater than 4 and 8 minus 2x for x less than 4. And we can see that this function is not defined at x equals 4. But even though it's not defined at that point, it is still possible for us to find the limit as we approach that point. So we have the limit as x, again, because it's piecewise, we're going to look at the limit from above and the limit from below. It doesn't matter which order you do it. Let's do the limit from above first this time. So the limit as x approaches 4 from above, so from the positive side of f of x. Okay, so as we're bigger, when we are greater than 4, the function that's operating is our, so we have our, we're approaching 4 from above. This is the function that is operating, that this function is equal to when we are bigger than 4. So that's the subdomain we're looking at. So in that whole subdomain, that's what f of x is equal to. So that is the function that we will use. So this is equal to the limit as x approaches 4 from above of radical x minus 4. Okay, so when I plug in 4 just above, so notice I couldn't even take the limit as 4 from below because something a little smaller than 4 minus 4 would be negative. We can't take a radical of a negative. But since we're approaching 4 from above, I can. Something a little bit bigger than 4 minus 4 is going to be getting closer and closer to 0 the closer I get to 4. So my limit here is equal to 0. Okay, and you can think of it, if you like, as 0 plus. We're approaching 0 from above. Okay. Similarly, we're going to now do the lower limit. So the limit from below, the limit of f of x as x approaches 4 from below is equal to the limit as x approaches 4 from below. This time we're using the other function because when we're less than or equal to 4, our function is 8 minus 2x. So anything that is below 4, that's the function that is in the domain that we are looking at. So we have 8 minus 2x. Okay, when we plug in something that's just a little bit smaller than 4, we are going to be approaching 0. And similarly, because this is a little smaller than 4, 8 minus it is going to be a little bigger, so we're sort of approaching 0 from above. It doesn't really matter whether you're approaching 0 from above or below as long as you have the same value, but here we do, you can see, have the same value. Okay, so the limit of f of x as x approaches 4 equals 0, even though f of x does not exist at x equals 4. So it doesn't actually even need to exist. Let's take a quick look just at what that function would look like if we graphed it. So we would have at x equals 4, we would have a hole here. We would have a radical function going up, and then we would have a y-intercept negative 2x plus 8. So our y-intercept would be positive 8, and then the x-intercept would also be 4. So we would have a line going up like that. And that's what our function would look like. So the limit is still 0, and you can see both of them are approaching 0 from above. Okay, so let's look at another rational function. Okay. And we had said that if we want to look at rational functions, we're going to try simplifying by factoring. So we have, let's find the limit as x approaches 3 of x squared minus x minus 6 over x squared minus 3x. Okay, so the first thing we do is we try. So 3 squared minus 3 minus 6, 9 minus 6 equals 0. And we also get 3 squared minus 3 times 3, 9 minus 9, also equals 0. Okay, so notice I'm not making this into a fraction and I'm not making the limit equal to it. This is just my test to show that we have indeterminate form. 0 over 0 is indeterminate. Okay, note if just the bottom equals, just the denominator equals 0. Okay, if denominator equals 0 and the numerator not equal to 0, then the limit does not exist. Okay, so if only the denominator is equal to 0, we just say the limit doesn't exist. But if they're both not equal to 0, that means there's probably something we can do to see if we can get a value for this. So this is equal to the limit as x approaches 3 of the same thing factored. Notice I keep the limit notation until the moment that I'm going to actually plug it in. So I have x minus 6, so we're going to get x minus 3 times x plus 2 over x times x minus 3. And we can notice here that the x minus 3's will cancel. So this is equal to the limit as x approaches 3 of x plus 2 over x. This is fine. X at 3, we no longer are getting a 0 over 0. And notice, if only the denominator stayed 0 and the numerator didn't stay 0, we would still have a limit that doesn't exist. But this limit does exist, so now I can plug in. So this is 3 plus 2, which is 5 over 3. And that's our limit. So again, this would have a removable discontinuity, or a hole at 5 over 3. Okay, well, that pretty much does it for regular rational functions. Those are fairly straightforward. You factor, you cancel, you plug in your number, you get your limit. What if there's multiple fractions? That gets a little more interesting. So let's say we have the limit as x approaches 1 of 1 over x minus 4 plus 1/3 over x minus 1. Okay. Well, we can see that 1 minus 1 certainly equals 0. And then 1 over 1 minus 4 plus 1/3 is going to be 1 over negative 3 plus 1 over 3, which also equals 0. So we have an indeterminate. So now we have to figure out something to do. So what I would try doing is try getting rid of your fractions in the numerator by adding them together, then you can divide. You can also divide first, make sure you're doing it to both pieces, and then multiply. It's just some fun with fractions. So what we're going to do is we're going to write the limit as x approaches 1 of 1 over x minus 4. We're going to multiply this 1 by 3 over 3 plus 1/3 times x minus 4 over x minus 4. Being careful. We'll just leave that all over x minus 1 for now. So we're taking the limit of that whole thing. So we are going to get 3 in the numerator. We have the same denominator. We're going to get a 3 plus x minus 4. Okay. So this is the limit as x approaches 1 of 3 plus x minus 4 all over 3 times x minus 4. We have the same denominator, so we can just add. And all of this is divided by x minus 1. Okay, so let's simplify and then rewrite this as multiplication. So this is still, notice I still have all my limits. So this is still the limit as x approaches 1 of x minus 1 over 3 times x minus 4 divided by x minus 1, which is the same as times 1 over x minus 1. And I notice I have the same thing here in the numerator and denominator, so I can cancel. So this gives me the limit as x approaches 1 of 1 over 3 times x minus 4. And when I evaluate this limit, this is 1 over 3 times negative 3, which is negative 1/9. When I plug in my 1. So that limit does exist. Okay, let's see one more like that, because as we know, fractions are so much fun. So we have example 8. Let's look at the limit as x approaches 0 of 1 over x minus 1 plus 1 over x over 2. Okay, well, let's see. 1 over 0 minus 1 plus 1 is equal to 0. 0 over 2 is also equal to 0, so this is indeterminate. So that means we need to do some stuff before we're going to be able to make this come out. So this is equal to the limit as x approaches 0. We are going to add these to each other. So this is 1 over x minus 1 plus x minus 1 over x minus 1. We're multiplying numerator and denominator of 1 by x minus 1, so we can actually do our addition. All of that over x over 2. So this gives us the limit as x approaches 0 of x, so 1 plus x minus 1 is just x, so x over x minus 1, and all of that over x over 2. So now we are going to actually do our division. limit as x approaches 0, we are going to divide by x over 2, which is the same as multiplying by 2 over x. So x over x minus 1 times 2 over x. Our beautiful x's cancel, and we get that this is the limit as x approaches 0 of 2 over x minus 1. You are allowed to shorten some of these algebraic steps. Just make sure that you're doing it properly the whole way through. So we get that this limit, when we plug in 0, this is equal to -2. Okay, so what happens, okay, if you can't simplify as above? Okay, so by factoring or by dealing with some fractions and simplifying as much as you can. So factor or add, subtract rational expressions, okay? What you're going to do, there are two things. So number one is look for special cases. And there's two special cases that we are going to look at. So our special case A is for absolute value. And we are going to rewrite these as piecewise functions. And we looked earlier at how we deal with piecewise functions. Okay, and if it's a regular absolute value and your limit exists, that's going to be pretty helpful. It's only the case where you're going to need to do this is if you wind up with something indeterminate with an absolute value. Most absolute value limits, you probably could just plug in your number and get your answer. That's okay. So do remember that our absolute value function in piecewise form is equal to x when x, whatever is inside the absolute value, is greater than or equal to 0, and negative that stuff when you have x less than 0. Okay, so what kind of function could they, absolute value function, could they possibly give us that's going to give us a 0 over 0? Well, this one is a lovely little classic. So we have the limit as x approaches 3 of the absolute value of x minus 3 over x minus 3. Interesting. So as we approach 3, the absolute value of 3 minus 3 equals 0, and 3 minus 3 also equals 0. So we have an indeterminate form. So if it's not indeterminate, you don't need to bother with writing the absolute value in piecewise function. As in piecewise form, you should be able to just get your limit. So here we want to do this. So we're just going to write the numerator in piecewise form. So the absolute value of x minus 3, we want it to be, we want to look at where it's positive. So where it's positive, it gets left alone, just as x minus 3, and it's positive when x is greater than or equal to 3. And it is negative, so it gets negated, negative x minus 3, when x is less than 3. Okay, so like, for example, if x were 2, we would get negative 1 or positive 1, which is what the absolute value does. So now that we have it in piecewise form, we have a piecewise function that switches at 3. So we're going to need to look at a left-hand limit and a right-hand limit, or a limit from above and a limit from below. So the limit as x approaches 3 from below of f of x equals the limit as x approaches 3 from below of negative x minus 3 over x minus 3. Okay, and we can go ahead and, as this is factored, we can cancel it, but we're left with a 1 in the denominator and a negative 1 in the numerator. So this is equal to negative 1. Okay, and we can label this LS for left-hand side or limit from below, whatever you like. So from the right side, or the limit from above, so as we approach 3 from above, the limit of f of x is equal to the limit as x approaches 3 from above, where we have the other function in operation, we're leaving it alone. So x minus 3 over x minus 3, which cancels, leaving us with 1. So as we approach 3 from below, we're heading to -1, and as we approach 3 from above, we're heading to +1. So because these two limits, these are, we've been seeing that these are the same. These are not the same. Okay, and in fact, what this function looks like when we actually graph it is we have, it's going to be 1 for everything that is greater than or equal to 0. So it looks like that. And it's going to be -1 for everything less than 0. Okay, because each side is approaching a different number at different times. So, and at x equals 3, it actually just doesn't exist at all. Sorry, this should be x equals 3, not 0. Silly Missy. Okay, so as we're approaching 3, that's what's happening. This is our y-axis. So the graph doesn't exist at 3. Anywhere above 3, it's going to be +1. Anywhere below 3, it's going to be -1. Okay, so with all of that, the limit as x approaches 3 of f of x, it's approaching two different numbers, so that limit does not exist. Okay, special case B, everybody's favorite, radicals. Totally radical. So we have a strategy for radicals when we wind up with an indeterminate form, so 0 in the numerator and denominator, and that is multiply by the conjugate. And that gets into some very interesting algebra sometimes. So, example number 10. We have the limit as x approaches 10 of radical x plus 6 minus 4 over 10 minus x. So radical 10 plus 6 minus 4, that's radical 16 minus 4 is equal to 0. 10 minus x equals 0. So we have indeterminate. They're both 0. We would have a 0 over 0. So what we're going to do is we're going to multiply the numerator and denominator by the conjugate of the radical expression. It doesn't matter whether the radical expression is in the numerator or the denominator. So if we have radical x plus 6 minus 4, that means we're going to be multiplying everything by radical x plus 6 plus 4. Okay, and we have to do the same to the bottom. So we multiply by radical x plus 6 plus 4. So let's expand our lovely brackets. I'm not going to expand the denominator because I probably won't need to. So we have 10 minus x in the denominator, so this is the limit as x approaches 10 of x plus 6 minus 4 radical x plus 6 plus 4 radical x plus 6 cancels, minus 16. Okay, and this is over 10 minus x. 10 minus x times radical x plus 6 plus 4. Again, we don't need to expand the denominator because we're going to be plugging in 10 if we can get this to cancel. So we have limit as x approaches 10 of x minus 10 over 10 minus x times radical x plus 6 plus 4. So we can cancel this. It leaves behind a -1. And so we get the limit as x approaches 10 of -1 over radical x plus 6 plus 4. So this is -1 over radical 16 plus 4, which is not going to be 0 in the numerator or the denominator, which gives me -1/8. And so those are a number of the different kind of situations you'll be encountering as you try to algebraically evaluate limits. Please remember, the cases in which you really need to do something are the cases where you wind up with an indeterminate form, 0 over 0. If it's something over 0, it does not exist. If it's an actual number over 0, it doesn't exist. And if it works out to a numerical answer, there's your answer.